Hi, Year 12. This is a voluntary tutorial for week 2, term 4, and I'll be going over methods of determining reactions on beams, and I'll show you analytical methods and a graphical method if you've only got 3 forces acting on the beam. This first question that I'm going to go over is on page 93 of your red workbook, and it asks you to find the reactions on this beam with 2 external loads here. The important thing to know about finding reactions is you've got to determine what force is acting on these 2 different sorts of reactions. Now, this is called a roller reaction, and the only reaction that can act on a roller is operating at always 90 degrees to the roller, because if you apply a force, a horizontal force to the roller, it will theoretically just roll along. Now, as you know, they don't use rollers now on beams. They use elastomeric bearings, or they use unidirectional bearings that we'll have a look at later in later lessons. And this is a pin reaction, and this reaction can resist a force in 360 degrees. So if you've got say a 10-ton truck braking on a bridge beam, this is the reaction. The pin reaction will prevent the beam from moving horizontally. And this reaction here prevents the beam from moving vertically. And you've got to have a moving reaction to resist the temperature stresses set up by expansion and contraction, and also concrete creep. So this beam should be able to move laterally or horizontally as a result of this sort of reaction here. To find the reactions, the first thing that you do, there are 5 steps that you'll have a look at here. There's the 5 steps. The first thing that you do with any of these questions, in my opinion, is to put all of the forces on the reactions. Now, if you put the vertical reaction here, which is going up, which opposes those 2 reactions for external forces acting down, and your horizontal reaction at this pin to resist the horizontal component of this inclined force here, the examiner will see that you know quite a bit about the reactions at a pin, and you'll get marks for it. The other reaction, of course, has to go at 90 degrees, and I would always advise you to draw a square there to show that that reaction always acts at 90 degrees to the surface. And this reaction is going up here to oppose those 2 forces going down, but there's cases where this reaction could be going down if you've got forces acting underneath there. But you've got to determine that yourself. So let's have a look at this. The first thing that I advise you to do is to take moments about the pin. And so you make this statement: sum of the moments about the pin equals 0 with clockwise positive. And you analyze this beam by using that formula. Now, make sure that you put this statement here equal to 0. If you don't put that there, the examiner will see that you really don't understand what this formula means here. So you've got 300 times 2, so you've got 300 multiplied by 2, that the distance back to the point of rotation, and it's going clockwise, so it's positive. Plus, I've broken this force up into rectangular components. Now, if you wanted to, you could just extend that down there like that, and you could work out this perpendicular distance there. if you didn't want to break this up into rectangular components. So, but I've broken this up into rectangular components, and so the vertical component of this force is 400 sine 60, and I'd advise you to work that out so you don't have to work it out down here when you're putting it into an equation. And the horizontal component is 400 cos 60, which is 200, but that goes through the pin, so the distance, the perpendicular distance of that force about that point is 0. Now, if you're not given, you can see that that force there is acting on top of the beam. Don't get worried when you see, oh, the pin is a little bit below it and you're thinking, oh, there is a perpendicular distance. If you're not given that perpendicular distance, they mean that the perpendicular distance of that force about that point is 0. It goes through it. So we've got 346 times 5. You've got to add the distance that force is away from the pin, and that's going clockwise, so it's positive. Now this force here is the moment of that force that will balance those two forces here. So you've got minus RR times 8. It's going to go anti-clockwise, and 3, 6, 8 is the perpendicular distance, equal to 0. Now, if you get a positive answer here, it means that you've used those signs correctly. And so the reaction is 291.5 kilonewtons. And that's the reaction at the right end of the beam. Now, you can see that that force plus that force has to equal that force plus that force to keep it in equilibrium. And so we're going to say the sum of the vertical forces equals 0 with up positive. So we've got RLY, which is the vertical component of this reaction here, and that's going up. We're assuming it's going up. If we get a positive answer here, it means that the assumption is correct. So we've got RLY going up, minus 300 going down, minus 346 going down, plus this force going up, and that equals 0. So therefore, RLY is equal to 354.9 kilonewtons. So that's the vertical component of that force. And you start for the third step, the sum of the horizontal forces equals 0, with that direction positive going to the right. And you don't need to write all that down. You can just say that that force there has to equal that force there, because there's no horizontal components with these forces here. So you can write it like this if you like, RLX going positive, minus 200, that force there is going negative, and it equals 0. So therefore RLX is equal to 200 kilonewtons in the positive direction. And the reason why you know that's correct is because you've got a positive sign there. You've interpreted that to be positive. If you said that that force is going in that direction, you'd get a negative answer here, and it tells you that you've assumed that incorrectly. So now we've got the horizontal component and the vertical component of this force, and we use Pythagoras because we have to get the reactions, right? Single reaction, one reaction there, one reaction there. If they ask you for components of the reaction at the pin, you only have to give them that and that. You don't have to use the next step, which is step 4, and to find RL and use Pythagoras. So you've got this set up here. You've got 354.9 and 200 there. So that squared plus that squared equals the square root of RL. And so you get 407.37. So RL is 407.37 kilonewtons. But that's not all. You've got to find the sense and the direction, and you know the point of application. So here we have theta there, tan theta is opposite over adjacent. So it's 354.9 over 200. So it's 60.5 degrees. And they will give you a position on the question where you have to put this information down. So, and there's the correct answer for that question. Okay, the next question I want to show you is one similar to that one, except it's only got 3 forces acting there. And I'm going to show you how to use the 3-force rule to work out what these reactions are. So I'll just go through the analytical process again very quickly, and then I'll show you how to do the 3-force rule to determine the reactions. And you'll see that the 3-force rule is much easier than this, unless you're interested in doing it mathematically. You'll get exactly the right answer mathematically, and but if you do it graphically, as you know, you'll get a tolerance of 10% leeway on your answers. So first thing you do is you put down all of the forces that are acting on this beam here. I've just drawn it freehand there, and I haven't put RL in there, but I should have put RL just in there. So you take moments about the pin. Always take moments about the pin, unless you are only asked to find the components of the pin or the force in the pin. So my advice is always take moments about the pin unless you've got a strange question. So you say some of the moments about RL, so I've got 346.4, which is the vertical component there, minus RR times 8, so you get 216.5 there. And see what I got here, it's pretty close. It's well within 10%. And then some of the horizontal forces, so you've got that force equal to that force, which we've just done. Vertical forces, same routine. So we've got the horizontal force and the vertical force there. You put it together like this so that you understand that that squared plus that squared will equal that squared. And that's what we've got here. So we've got 238.5 kilonewtons. And the graphical method gets 232, which is pretty close. And then you've got to find theta there. Tan theta is equal to opposite over adjacent, which is 33 degrees, which is exactly what I got here. So let's have a look and see how you do it graphically. Now, the first thing you've got to do is count the number of forces. If there's only 3 forces acting on the beam, you can do it graphically. If there's 4 forces, you can do it, but it's a lot more difficult, and I don't want to show you that. If there's 4 forces, you've got to use this method here, the analytical method. So the first thing that you do is you've got to find this point of concurrence. And so you know that that force goes vertically up, and you're using your set squares. Make sure you line your set squares up on the horizontal line, and you've got 90 degrees on your set squares, so you can draw this line in accurately. Draw it up there, and then this line here, you just extend it. That's 60 degrees. 60 degrees goes up, and where the two lines join, that's the point of concurrence, and you know that this force will join that point there. And so you've got this this arrangement of forces on the diagram which all converge at this point of concurrence. Now, the next thing that I do is I use Bose notation. So I've got A around there, you read it clockwise, B in there and C in there. And you organize a scale and this is a convenience scale, 400 equals 100 millimeters. Just make sure that it will fit on the page. You can adjust your scale so it'll fit on the page, and make sure that your force diagram obeys the hole in the hand rule. I've shown you that. If you get your second finger next to your index finger and your thumb, make a hole. The force diagram has to be bigger than that hole that you've made with your finger and thumb. So we've worked out 1 millimeter equals 4 kilonewtons. So this force here will be represented by 100 millimeters. So I've measured from there down to there, and that's 100 millimeters. You put your sense on it, because it's shown you there how the sense goes. And this force, reading it clockwise, is BC. So I've put little b up there and little c there. Now, reading it clockwise, the next force you come to is CA. We've got C there, so you transfer that angle down there using your set squares accurately, and then you draw that line up there. Now, where it hits the vertical force there, this force here will be CA, and where it hits that vertical force, that'll be A, and this force here, going up and down there, will be AB. And so it's got to go through B up there. And so the red is your force diagram. So using that scale, you measure this distance from there down to there, and that works out to be 55 millimeters. You multiply it by 4, and you've got 220 kilonewtons, which is pretty close to 216.5 kilonewtons. Then you measure this distance from there to there, and that works out to be 58 millimeters. And then you multiply that by 4 up here, and that gives you 232 kilonewtons, which, as I said before, is pretty close to that. But that's not all. With this force here, with RL, you've got to put the direction, which is the angle, the sense is the arrow, and the point of application. So you put your protractor on here, you measure that angle, and you see there's 33, which is exactly what we got analytically. Put the sense is shown by that there. Of course, all these forces go in the same general direction because the beam's in equilibrium. And your point of application, which is RL, and you've shown where RL is on the diagram. If you don't show that, they won't know where it is. So make sure that you're consistent. So there's the two ways of doing it. Now, don't forget, you can only use this method when using the 3-force rule, when you've got only 3 forces acting on the body. Now, I'll show you an HSC question now where you could use that method. And here's an HSC question. You haven't done trusses yet, but they're exactly the same. Finding the reactions are exactly the same method for trusses as you use for beams. So there you've got a pin there, and you've got a roller there. And same routine here. I won't go through that with you because I've just been through it. And also, I will be doing that when we're doing trusses. But I just want to show you down here how you do the 3-force rule, use the 3-force rule to work out what the reactions are. So you know that you've got your force going down there, you've got a force going through there, and you know that you've got to have a force at 90 degrees to that surface there. So you know the direction of that force is vertical. We don't know whether it's going up or down yet, but you can just see that it'll be going down because it's got to oppose that motion there. So what you do is you work out your scale, which I've worked out here, 1 kilonewton equals 1 millimeter. Use Bose notation, A, B, C here. And the only force you can start with is this force here, 100 kilonewtons. And so where you have this force goes up and that force goes there, so you've got your point of concurrence, and so that force has got to go through there. So that's the direction of that force there. Straight away, you've got that with little working. And so you go from the point of concurrence down collinear with that force, and you go down according to your scale. You go down 100 millimeters, and then you mark it there. And that force is BC, so you mark it B and C. And the next force is CA, and it's got to go through C. Now, we don't know whether that goes up or down, so you just draw it in. And we know it goes up because it's got to hit this next force there, because there's only 3 of them. And we know that this force is CA, it's got to go through C, and it's got to hit this force at point A. And then this last force is AB. So we've got A, B's got to go, this force has got to go through B. So there is your force triangle there. And then you just measure this distance here, and that will give you the magnitude of RL. You measure that angle there, and that will give you the direction of RL, and you see that sense there, and that will give you the sense of RL. And this distance here, from there to there, that will give you the magnitude of RR that's going up. So, I mean, this is okay, but you can get bogged down with maths. But this method is a very simple method, but you've got to practice it. Okay, I hope you understand that, and I'll send this recording to you tomorrow. Bye.